Let's say that two movie theaters sell a mean of 500 tickets on Mondays with a standard deviation of 50 tickets. On a certain Monday, movie theater A sold 700 tickets and movie theater B sold 510 tickets. Which movie theater performed better that Monday? Well, movie theater A, since it sold more tickets than movie theater B. We can also look at it as the number of tickets sold by movie theater A has a greater distance above the mean. If we look at it like this, we can also see that movie theater A sold a significantly high or an extreme number of tickets that day. Let's change up the question a little bit. Let's say that movie theater A is a small mom and pop theater, and they sell tickets with a mean of 100 tickets and a standard deviation of 20 tickets on Mondays. Theater B is a franchise, and they sell tickets on Monday with a mean of 7,000 tickets and a standard deviation of 600 tickets. On a particular Monday, Theater A sold 145 tickets, and Theater B sold 8,145 tickets. Which theater did relatively better that day? Well, it's true that the franchise sold more tickets, but success is relative. Remember that, success is relative. I'm dropping knowledge here. To see who did relatively better, what we do is compare the number of tickets sold to their individual mean and standard deviation. Notice how they both fall above the mean. However, this is where they start to differ. Theater A falls 2 standard deviations above its mean, and Theater B falls just under 2 standard deviations above its mean. Since A is more standard deviations away from its mean, it has performed relatively better than Theater B. Instead of drawing pictures to compare their relative success, there is a better way to quantify this. We call this the z-score. The z-score is a number that tells us how many standard deviations a data value is away from its mean. A z-score of 0 means that our value is the same as our mean. A z-score of 1 means our data value is 1 standard deviation above the mean. A z-score of -1 means that we are 1 standard deviation below the mean, and so on and so forth. Let's find the z-score for this example. Fill in the mean and the standard deviation for Theater A, then replace x with the data value in question. We do the same for Theater B. And now we can compare who did better. Since Theater A's z-score is larger, it has outperformed Theater B. Here's another example. A basketball team scores a mean of 90 points a game, with a standard deviation of 11 points. The mean weight of a pumpkin is 9 pounds with a standard deviation of 2 pounds. If the basketball team scored
50 points,
78 points, and a picked pumpkin weighs 4.8 pounds, which of the two is more extreme relative to the data set from which it came? Let's compare these two values using the z-score. Since a z-score of minus 2.1 is further from the mean, we would say that the weight of the pumpkin is more extreme. Notice that when we use z-score, we are essentially stripping our data values of its units. This is the only reason why we are able to compare the two data values. It's like you were trying to compare the value of an orange to that of an apple. Instead of trying to literally compare apples to oranges, we compare them on some other common unit such as the dollar. When we consider their dollar value, it's much easier to discern their difference in value. So, when we use z-score, we are stripping our data of its units, such as points and pounds, and putting them on a comparable unit, which is the number of standard deviations away from the mean. Before we compare any two sets of data, we must always strip them of their units and compare them on a level plane.